All right, let's look at a problem here where we're trying to find the limit as x approaches 0 of the absolute value of x over x. Now, when we're evaluating limits at real number values, we're always hoping for continuity. And if we try to plug 0 into this expression, we get 0 over 0. And with limit talk, we're talking about an indeterminate form here. So in this case, we would like to figure out another way to tackle this limit. We do get the 0 over 0. Now, I also see that we've got an absolute value in this expression. So let's try to get rid of the absolute value part and see if that helps us out in answering that question. So I'm going to kind of keep this stuff up to the top here, and I'm going to take this absolute value of x over x, and I'm going to make it piecewise and see if that helps us out in determining the limit. First off, I'm going to name it f of x. So if we have f of x equals the absolute value of x over x, I want to take that and make it a piecewise function. In order to do that, I need to determine the critical value for the function. And the critical value for this function is going to be determined by what's inside the absolute value. Now in this case, it's only x inside the absolute value. So when x equals 0, we have a change in behavior of this function. And it's a coincidence. It was x equals 0 up here for the limit that we were evaluating at. So I've got 0 here, that's my critical value. What that tells me then is I've got behavior to the left of 0 and behavior to the right of 0 for this function that I have named f of x. Okay, so when we are to the left of 0, we can use test points, we can plug in values, anything to the left of 0, and determine what the absolute value does to those numbers that are to the left of 0. Okay, and if we're to the left of 0, that means we're plugging in negative numbers, and if we plug in negative numbers here, the absolute value takes the opposite of them. Now, we can take the opposite of numbers without the absolute value sign. We can use a negative sign. So what that means is f of x to the left of 0 behaves like opposite x over x. When we are to the left of 0, the critical value of 0 here, we plug in negative values. The absolute value makes them positive. It takes the opposite of them. So I'm going to take the opposite of them, not with the absolute value sign, but with the negative sign. So to the left of 0, this function is opposite x over x, which cancels to -1. Okay, what about then to the right of 0? Well, if we're to the right of 0, we're going to plug in positive values for x. The absolute value is not going to do anything to the function to the right of 0. So that means f of x equals x over x, which will reduce to 1. What that tells me then is that we have this function f of x, which equals the absolute value of x over x. I could rewrite this function into two pieces. -1 and 1. When we are to the left of 0, we're at -1. When we're to the right of 0, we're at 1. And I would say when x is less than 0, when x is greater than 0. Now in this piecewise function, I am not going to include the 0 in either one of the definitions, because this discontinuity where 0 is in the denominator, there's nothing that we can do about that. But we do have a piecewise linear function with a jump at 0 in this case. So if we were to graph it, we would have add 0, open circle, line at 1, open circle -1, line at -1. Graphically speaking then, we can see that if we were trying to calculate a double side limit here at 0, we've got what's called a jump discontinuity. That tells us then the double side limit does not exist. I'll use DNE to abbreviate that. And I'm going to explain a little bit better that -1 does not equal +1, which tells the reader that we've got a jump discontinuity there at 0. This double side limit at 0 for absolute value of x over x does not exist. We determine that by making it into a piecewise function, in this case a piecewise linear function. Even though it's in a piecewise function format, it's still discontinuous at 0. Okay.